Here we go. Onto the bulldozer. All right, so we have a bulldozer, mass big M, and it's pushing a cube-shaped rock, bizarre, of mass little m across a rough ground. All right, rough ground. Here's the thing. This is a big hint right here. Rough ground. If we have a smooth ground, a smooth surface, that means there's no friction. But if it is rough, that means friction is going to happen somehow, some way in this problem. So that's a big clue right there that we're dealing with a force problem. If we are dealing with a force problem, then first thing we do is we start with a free body diagram. After we get our free body diagram correctly drawn and labeled, then we'll go to a Newton's second law equation, the stuff that makes it go minus stuff that holds it back equals mass times acceleration, and then we're going to solve probably for acceleration, or we're going to solve for one of the forces acting on the thing. So I don't even know what the question's asking me yet, but because I've identified that friction is involved and I know that friction is a force, I'm going to deal with this by solving the problem as a force problem. Okay, so drawing part A, bulldozer and rock are speeding up. That's going to be important. So we know that acceleration and velocity are in the same direction. What am I even doing over here? All right, so velocity that way, acceleration that way. Speeding up. All right. Let's think about this. Forces acting on the bulldozer. We'll do the easy ones. We know the bulldozer is on the ground and it's not sinking, so it's got to be... Those two forces are going to cancel each other out. 1, 2, 3, 4, 5 boxes down, 5 boxes up. And we have the weight force of the bulldozer. And then we have the normal force of the earth on the bulldozer. Then we can see there's a contact happening here. So we have a normal force from the rock on the boulder pushing that way. So we'll have this, let's say, so this is the rock on the boulder. Rocks and boulders are very similar. But in this case, we're talking about a bulldozer, Mr. Escapetus. So this is the rock on the bulldozer. Is that it? That can't be it, because we're moving to the right and we're accelerating to the right. So this bulldozer better have some kind of rightward force. Well, what is making a bulldozer go? What's making a bulldozer go forward is the same thing that makes you walk forward. Do I need to take off my shoe again? So we'll have friction pushing us in this direction. Forces on the rock. Well, it's got some kind of weight that is definitely smaller than the bulldozer, right? Because big M and little m. And it's not sinking, so we went down 3, so we're going to go up 3. And we're going to call that the normal force, the earth on the boulder. Then we have this same normal force. This is Newton's third law. Force pair reaction, equal magnitude, opposite direction. So we have the rock on the boulder. Well, we have the boulder on the rock. I keep saying boulder. Like, I don't know what the word bulldozer is. I'm so sorry. Here we go. Continuing on, Mr. Escapetus and his follies. All right, then we also have friction. Now, is this a force pair? Is this a Newton's third law situation? No, because friction is the ground acting on each of these objects independently. So this frictional force here is going to be smaller than this frictional force over here. So think about it. We have frictional force equals mu times the normal force. And we know the normal force is mass times acceleration due to gravity, so it's mu times mg. So our frictional force equals mu times mg. If we increase our mass, we're increasing our frictional force. We obviously have a larger mass with the bulldozer than we do for the rock. So what about the external forces acting on the bulldozer cube system? Well, For that, we're going to look at everything acting. So we have the weight force for the entire system, which we call FW, and opposing it is Fn. Yes, they're equal and opposite, both go up. Now we have this frictional force forward and a frictional force backwards. That's kind of sloppy, right? So instead, I'm going to say this is a force of the ground on the system, and then we have a smaller frictional force to the back, because remember, we're dealing with a rough ground. So that is where the rough ground is coming in. It's that frictional force that's preventing any of the sliding, because that's what friction does. It prevents sliding. All right, in the blanks above, write an equation stating Newton's second law for the bulldozer, rock, and the combined system. So then determine the acceleration of the bulldozer rock system. If the mass is 1,000 kilograms, mass of the rock, okay, this is a lot. So first, I'm going to change colors here, and I'm going to do my Newton's second law equation for the forces on the bulldozer. Stuff that makes it go is going to be that force of the ground on this guy right here. Ground on the bulldozer. That's what's making it go. Whatever you want to call that. Friction, force of the ground on the bulldozer, whatever you want to call that. Minus what's holding it back, the force of the rock on the bulldozer. Equals mass times acceleration. For this one, things making it go, well, we still know that it's going to the right, so it's the force of the bulldozer on the rock minus this frictional force equals mass times acceleration. And for this one, the force of the ground on the system minus our frictional force equals mass times acceleration. That's going to allow us to do kind of a shortcut here to determine the acceleration of the boulder rock system, because we're just looking at everything as a system. We don't care about the interaction between the boulder and the bulldozer and the rock. All right, so mass of the bulldozer is 1,000 kilograms. Mass of the rock is 500 kilograms. Friction on the bulldozer is 5,000 newtons, and the force of friction on the rock is 2,000 newtons. So that friction of the rock, that's this guy right here. So this equals 2,000 newtons. This one equals 5,000 newtons. So that means this is 2,000. This is 5,000. So stuff that makes it go minus stuff that holds it back. We'll go to red. We have 5,000 newtons minus 2,000 newtons equals mass of the system. So it's mass of the bulldozer and the rock, 1,500 times acceleration. Dividing that out, we have 3,000 newtons divided by 1,500 newtons, or excuse me, 1,500 kilograms equals our acceleration. So we get an acceleration of 2 meters per second squared.